Good morning, my name is Devolder and I'm happy to present our work on the backhopping in STTMRAM cells. This is a joint work between my group in Palaiseau, this is Paris area, France, and IMEC. We work with perpendicularly magnetized tunnel junctions that are switchable by spin torque. That is to say that their resistance versus voltage can be switched from the low resistance parallel state to the high resistance anti-parallel state using conventional Schlonchevsky torque. And this is what I will call the normal behavior of STT switching. If you have a junction like that, then the right error rate is monotonic with the applied voltage. That is to say, when increasing the voltage, you have switching probability 0, and then it increases and goes asymptotically to 1 if you increase the applied voltage. So there's always an interest to increase the applied voltage to have the switching faster and more reliable. Unfortunately, for some of the junctions, it doesn't happen like that. There is what is called the backhopping. Instead of having the normal behavior, you have a different behavior where if you go on further increasing the applied voltage, suddenly the right error rate increases again, so the probability of switching decreases despite the fact that you're applying a higher voltage. This can be seen in right error rate measurements, but this can also have signatures in resistance versus voltage loop, either at high voltage or at high temperature. And what you can see in these loops, that if you increase the voltage starting from 0, you first can induce, for instance, the P to AP transition, the normal one, but if you go on increasing the voltage to unreasonably high level, you switch to a different state that I will call the P prime state, and which is not the state that you intend to write. So people have searched for an explanation for this backhopping phenomenon, and the historical explanation was a story of the bias dependence of the Schlonchevsky torque in tunnel junctions. The bias dependence of the torques were calculated by Theodonis and co-workers some time ago for different material parameters. And for the most reasonable material parameters, this is the blue curve, at negative bias, we had a positive torque, so inducing a given transition, while at positive bias, when the bias was low, there was the normal torque, inducing the switching that you expect. But as you can see, if you increase the voltage too much, the torque decreases and finally even reverses. And so people have thought that the combination of this unconventional voltage dependence of the torque and of a large field-like torque in the junctions could be responsible for this backhopping phenomenon. And indeed, as shown by Skowronski some time ago, this explanation reproduces some of the qualitative features of backhopping, and it might be reasonable to think that at reasonably low bias, you induce the normal transition, but if you go on increasing the voltage, the torque decreases, and you come back to the initial state because the torque has changed sign. To test whether this historical explanation is correct, we can rely on the material dependence of the bias dependence of the torque, because indeed the way the torque depends on the voltage should depend a lot on the chemistry of the free layer. So this is what we're going to test first. So we will work with magnetic tunnel junctions having various free layers, but sharing in common that they all have the same fixed system, which is a conventional, usual reference layer comprising a cobalt iron boron part responsible for the spin polarization and a synthetic anti-ferromagnetic part in order to have good compensation and strong rigidity. And below this common fixed system, we've grown several free layers, the standard ones, which are the dual MgO free layers, but also hybrid free layers, where you have a texture transition layer in the middle, thanks to a tungsten spacer, a tantalum spacer, or even we've investigated more fancy free layers having a high volume and a low moment. And in order to test whether there is backhopping in these junctions, we perform the following experiment. We apply voltage pulses on the P state in order to try to induce the AP transition, and we monitor in real time the device conductance in order to identify when it switches, how it switches, and what else, everything else that can be seen. And indeed, if you work in normal conditions, the voltage pulses do trigger the parallel to anti-parallel transitions after some nanoseconds. If you increase the voltage, it goes faster, but the problem comes if you let the current on for a long time. And then what can happen is that after some time, the system seems to switch back to backhope in a state that looks like the initial state. And here I show the case for this high volume, low moment free layer, but in fact this is happening for all the free layers that we've attached to this fixed system. So we conclude that backhopping is not a story of the free layer, it's a story of this fixed system. Okay, so the historical explanation has to be revisited. And for this reason, we perform this time-resolved experiment in a more detailed manner. Okay, and the question we want first to answer is whether the state that appears at the end of the measurement, this P prime state, is it the real parallel state or is it something different? So let's perform single-shot large bandwidth measurement. We go from P to AP and we let the current on and it switches to a final state. And you might see in this high bandwidth measurement that the resistance of the final state is not exactly the same as the initial state. But of course there is noise, so you can argue that maybe this is noise related. But then you can perform the experiment many times and see that it's systematic. And if you are still not convinced, you can do the measurement with a lower bandwidth or a higher resolution. And this indeed proves that the conductance of this final P prime state is definitely not the one of the P state. Okay, so this P prime state doesn't exist at remanence. There's no state at remanence that have a resistance close to P but different than P. So let's try to identify the nature of this P prime state. So we restart from the MTJ composition, remembering that there's an FCC part, a BCC part, separated by a texture transition layer that provides also ferromagnetic exchange coupling. But the ferromagnetic exchange coupling between the two parts of the reference layer is only a few tenths of millijoule per square meter, so it's indeed the weakest coupling within the stack, the weakest exchange coupling within the stack. So of course in this stack we have the stable state, parallel and anti-parallel state, but you can think of additional states where you frustrate the exchange at this texture transition layer. And I will call them the P prime state and the AP prime state. The P prime state is a state where there is frustration at this texture transition layer because the top part is magnetized anti-parallelly to the bottom part. And same for the AP prime state. And they are named P and AP because the Paris-facing layers have parallel orientations or anti-parallel orientations. And if you look at their transport properties, you realize that these states, the thickness, the total thickness where the magnetizations are parallel is less in the P prime state than in the P state. So because the thickness of the parallelly aligned layers are different, you expect a slightly different array product and a slightly different TMR, as shown some time ago in the group of Dieny. So this brings us to the conclusion that we think that this P prime state is a state where you have selectively switched the spin polarizing part of the reference layer. The question is now what happens to this P prime state? Is it stable? What happens then? There are three cases that can occur. In what I've showed so far, the P prime state seems stable and stays forever, except if you remove the current, and in this case it relaxes to the AP state, which is the intended state. So in this case there is some unwanted dynamics, but there is no write error because this state switches to the state that you intend to write. If you increase the voltage or if you go to different free layers, then you can have situations where the P prime state is very noisy And if it's noisy enough, it's going to switch to a different state in a sequential manner that restarts forever. As for instance shown here for this tungsten hybrid free layer, where the p prime state switches to low resistance, high resistance, low resistance, high resistance, and so on forever. So the conclusion here is that the p prime state may or may not be stable, and in this case, if it's not stable, then you have a sequence of states that in which the system goes on as long as the current is applied. So if I summarize what I think happens during the backhopping sequence, we start from the parallel state, the conventional parallel state, and we switch to the AP state by switching the free layer easily because it's a good magnet with low damping and because the spin polarization is provided by the reference layer, which is a good spin polarizer. In order to switch to the P prime state, this requires a higher current because you switch this spin polarizing layer, which has a higher damping than the free layer, although you do it with a good spin polarizer. But so this happens at the threshold that is slightly higher than a conventional threshold for switching. And if you go on increasing the current, you will finally switch the free layer in this AP prime state, and you switch it thanks to the spin polarization of the reference layer, which in this case is a bad and inefficient spin polarizer because of its anti-parallel frustrated orientation. So this requires us to exceed a third threshold, which is the threshold where right error rates really happen. So a threshold for unwanted dynamics and another threshold for right error rates. And of course, this AP prime state is so frustrated that if you let the current on, or even if you remove it, it relaxes spontaneously to P, so that the sequence can restart over and over. So now that we think we've understood why there is backhopping, let's look at the material options available to try to suppress this backhopping phenomena. What is needed is to avoid the AP to P prime transition, and for this we need to increase the rigidity of the spin polarization layer of the reference system. And for this, the options are to increase the anisotropy, to provide more coupling through the texture transition layer, or to have a larger damping for the spin polarization layer. So let's look at the materials that are available for the texture transition. These are essentially refractory metals or alloys of refractory metals and cobalt, iron, boron. And if you look at the criteria, more coupling, more damping, and more anisotropy, they all converge to say that the foreseen best strategy is to have a texture transition layer that is based on an alloy of tungsten and cobalt, iron, boron. So this is indeed the best choice, and probably this is why it's empirically chosen in applications. So this brings me to my summary. I've talked about backhopping in STTMRAM, which can be seen either directly from right error made measurements or from resistance versus voltage loops as a new state occurring at high voltage. It happens within the fixed layer and not within the free layer. It's because the coupling within the fixed layer is sometimes not sufficient. You can view that in real time and identify the sequence of states that the system goes through and identify that there are two new states that have different resistances compared to P and AP. And finally, thanks to this understanding, we can speculate that the best material route is to go for tungsten, cobalt, iron, boron spacers as texture breaker ferrocoupler within the fixed system. And with this conclusion, I thank you for your attention.